If you recall, last week we were talking about integrals, specifically upgrading our integrals from functions of a single variable, where we were finding the area under a curve and above an interval on the x-axis, to a double integral, where we're trying to find the volume under a surface and above a region in the xy plane. Upgrading from curve to surface was not the interesting part. The interesting part is what happens with what we're plugging in. Remember the setup in the integral notation. We have this integral over r. This is all the stuff that we're going to be plugging into the following expression, f of xy dA. In this case, it's to find the volume underneath the surface f of xy and above the region r. So f of xy is the height, dA is the area. We just multiply the cross-sectional area by the height to produce a volume. In the same way that a function, the integral from a to b of f of x dx, the f of x was the height above some small interval dx on the x-axis. So the way the integral notation works is that f of xy dA is the expression we're going to be plugging a bunch of points into, and the integral over r is telling us what points to plug into that expression. Where this gets interesting is that instead of some boring old interval from the x-axis, we now have a two-dimensional region from the xy plane. And regions in the xy plane can have all kinds of different shapes. Intervals have only one shape. Now we have shapes only limited by our imagination. Yet despite that, we still use things like rectangles and circles and between a couple of functions. We can't go full imagination like right from the beginning. That's just insane. What we have to do, the skill that we're trying to acquire, is figuring out how to describe the region in the xy plane so that the integral will understand. Fortunately for our heroes, all we have to do is break it into pieces. What's x between? What's y between? Actually, what's x between? What's y between? I was using the wrong hand gestures earlier. I realized that they're not on the screen. But I was like, oh, what's x between? What's y between? So we're going to turn our double integral, our integral over r, into a double integral. So our integral over r, f of xy dA, will be a double integral, one integral for each of the variables. And because this is math class and we're trying to learn a thing, we have to do both. We get to describe the region as what's x between and what's y between. The order which we describe that is just whatever order is convenient to us at the time, or since we're learning both. So we can describe regions as dy dx regions with a dy dx or with a dx dy. Then we set up some rules for what has to happen. Whatever integral is going last, that is the first one we write down, which is the last one, the outer integral, the last integral only gets to use constants. Last integral only gets constants? The last integral only gets constants. The earlier integrals can use functions of upcoming variables. That's the way we were phrasing it before. The early integrals get to use functions of upcoming variables. The last integral only gets to use constants. What that means in our dy dx integral, since x is the last integral to go, that integral will have to be between two constants. So this would be the integral, say, from a to b. But the early integral, the y integral, could use functions of the upcoming variable. So y could involve some functions of x. In the case of rectangles, the first example that we did, the first example that all Calc 3 classes always do, those functions were just constants because we just had a rectangle, and a rectangle is just two intervals. But then we started breaking the rectangle up with lines. Today, we turn that up 1 degree. I'm going to make a rectangle, and then we're going to split it with a parabola. In the case of the dx dy integral, since y is our last integral, that would have to go between constants, say from c to d. The earlier integral, the x integral, can use functions of the upcoming variable. So I could have functions of y in the x integral. So this could say go from g1 of y to g2 of y. So we've got a nice simple strategy of what's x between, what's y between. How's everybody okay? Let's look at an example. Oh, also remember that the integration part is not the part that we're focused on right now. We've done one whole example where I gave you a function and you actually had to integrate the function with respect to x, then the function with respect to y, then switch the order, integrate with respect to y, then with respect to x. But we saw that that was just taking our partial derivative strategy and going the other way with it. The same thing that happened when we were learning to integrate functions. We just take all of our derivative stuff and do the inverse. That's not the interesting part. The interesting part here is describing the region for the double integral. Telling the integral what values of x and y you want to plug in to the expression f of x, y, dA, and then add up. That's the weird part, adding up this continuum. Where do you put the plus signs? We're trying to add all this stuff up. There's nowhere to put the plus signs because we have a continuum. but mechanically, the interesting part is describing the region. So let's come up with a region. I'm going to use a different one from last week, mostly because I don't remember the one from last week. So here we go. I am going to use the same strategy. I'm going to take a rectangle and we're just going to carve up the rectangle. So my rectangle, I think, is going to go up to 3. And then go, if I'm going to use 3, I'm going to have to go all the way out to 9. That's kind of annoying, but oh well. Last week, we cut the region in half with a line. This week, I'm going to take it up 1 degree, and I'm going to split this region with a parabola, but a sideways parabola. And I'm just going to, you could probably tell which parabola I'm going to use. Since x is 9, y is 3. I don't want a parabola that has 0, 0, and 9, 3. If I actually wanted to mess with you, I would have put the vertex at 9, 3 instead of 0, 0. But that would just, the only reason to do that would be to subvert the audience's expectations. And if the only reason that you're subverting the audience's expectations is specifically to subvert the audience's expectations, that's boring. That is played out. Don't do that. Do you know what I mean? It's not really clever anymore. Make sure you have a reason for subverting the audience's expectations. I'm going to use this function, this parabola, even though it is super basic. And this is the function y equals square root of x. The region that I want is the region above this curve and under y equals 3. So the boundaries are x equals 0, y equals 3, and there's my region. Same thing I was doing last week, only instead of connecting the corners with a line, I just push it into a parabola. Start with a line and just kind of shove, make a parabola. We're going to write 2 double integrals for this region, a dx dy and a dy dx. Friday, I think I did a lazy job of cleaning out my notebook. The ink just, or the gel does not want to stay. So we're going to make two integrals for this. A dx dy integral and dy dx integral. All we have to do is identify what's x between and what's y between, and make sure that we follow our rules. Our last integral only gets constants. Early integrals can use functions of upcoming variables. So let's do the dy dx integral first, because it looks like I wrote that one first. Even though I may have said dx dy first. I wrote the dy dx first. I can't remember. That was like a whole minute and a half ago. There's no way I can remember that. Since we know that the last integral only gets to use constants, that's the one that we should write down first. So the dy dx integral, x has to be constants. We just write the values of x were between 0 and 9. We don't worry about the shape. The last integral only gets constants. Just what values of x is the shape between. We'll only worry about left to right constants. In the second integral, I guess I'm going to mix and match. In the second integral, dy is the last integral. That means the y's are going to be constants. Just what value vertically, what values are the y between? That's 0 to 3. The last integral only gets constants. That's the one that we should write down first. Now, for the x is between 0 and 9, we got to think about what's y between. So we're going to pick a typical x value. And we're going to say, what's the lowest y value that we see in the region? And that would be the curve. And where do they stop? And that would be y equals 3. So we're going to integrate from the square root of x, because that's where we hit the region first for a typical x value. And we're going to stop when we get to y equals 3. And then we're going to do this for all the x's between 0 and 9. Even though we calculated dy dx, our thinking is kind of the other way around. For all the x's between 0 and 9, integrate from the square root of x up to 3. This happens a lot. If you want to describe the order of operations, like in a sentence, write down what the order of operations is and then speak it in reverse. Over in the dx dy integral, we've already said that we're going to integrate all the y's from 0 to 3. So if we pick a typical y value, we just write down the smallest x and then we write down the largest x. In this case, x is starting off at 0 down here on the y-axis and going up to the curve. Oh, but I can't write y equals square root of x. This is x. I have to turn our equation around to x equals y squared. So this curve, when we describe it, y as a function of x, we say y is square root of x. If we turn that into a function of y, x is y squared. So our smallest x value is 0, and our largest x value is the curve, x equals y squared. Once again, our thinking when we read it is for all the y values between 0 and 3, integrate from 0 to y squared. Any questions? How's everybody okay? I only ask because you're all looking at me like this. And I can't tell if that's because the problem's too simple and we've got this already, or you're just like, oh, I'm just going to ignore what's going on and then figure it out later. Which is a common strategy. Don't think you're unique in that strategy. So, well, I don't want to ask the teacher a question lest they think I don't understand what's going on. Never mind the fact that the teacher wants to know if you don't understand what's going on, because it's like literally their job to help you understand. But students are like, oh, no, I'm not asking questions. I'm going to wait till the one person whose job it is to explain shit to me is not in the room. And then I'm going to get really angry that I can't read my math book. I know some of you don't know what I'm talking about. It's like, oh, math class has always been easy for me. I don't have to study. Well, I'm not talking to you. But usually there's someone in the room that is really super pissed off when they try to figure out math. And one of the core reasons for doing that is that they try to do that when there's no one in the room that can help them. You know what I mean? I can totally understand why you wouldn't want to ask me. I'm the teacher. I don't answer questions. It takes me 10 minutes to answer a yes or no question. Like I said, about 5 minutes of information packed into an hour. But if that is describing you, or you think it might describe you in the future, like 2 floors up is the STEM center, that's where you should go. Because there are going to be people that know what the F they're talking about, or maybe even other students that don't know what the F they're talking about. And you can all sit there and say, man, Leach sucks. Let's figure this out together. Then you can like band together and figure some stuff out. And there's doors all over the place. So if you just sit at a table, both directions, you can have a view. So if you're worried, if you're going to talk shit about me, you can see the doors all over the place. I'm not going to be like secretly walking by. You know what I mean? It's like maybe you don't want to talk shit because you're worried that I might hear something. As if I don't know that you do. Like teachers that get surprised and I go, my students were talking shit about me. I go, yeah, they're your students. That's like one of the things that they're supposed to do. I mean, they're supposed to have enough tact not to do it in front of you, but I mean, don't be surprised when that happens. You know what I mean? And then teachers are like, oh, but I thought they liked me. It's like, oh, you are still the teacher. It's like natural enemies. I had a dog and a cat that lived in the same house, and they weren't like buddies, but they weren't like fighting. The dog knew that the cat would talk shit about the dog, and the cat knew that the dog talked shit about the cat. But they didn't do it to each other, you know what I mean? Decorum.
I got a question.
Then.
Yeah. So it says dA is region would be the dy dx or dx dy. So that's just the orange square you drew from 0 to 9 and 0 to y equals 0 to 3.
The square is just us trying to figure out what's the lowest value and the highest value. So I start at the lowest value of x and then end at the highest value of x. And then the green line is the lowest value of y and the highest value of y. When we think about dA, imagine looking, if we zoom in, imagine if we zoom in to one of these little dA squares. So we have an x-axis and a y-axis. So a dx is the same. It looks like a v over here. Why am my x's getting all fancy? There we go. Remember what we did in single variable calculus is we broke the interval up into a bunch of little dx's. all we're doing now is also breaking up the y interval into a bunch of delta y. And then if we find the intersection of these two intervals, that gives us this little square we call dA. Cool. So we're imagining that this weird parabola-sided triangle, I don't think we have a word for this. Maybe I just invented the word for this. This parabola-sided triangle is a bunch of little squares. And above each little square, I'm going to evaluate the function f of x, y. That's going to be the height. I have an area down here on the floor plus the height. And I'm just going to add up all those volumes. And then I'm just going to make the squares smaller. And then we're going to apply calculus. How small? Infinitely small. The same thing we always do in calculus. So yeah, thank you for that question. It's not this square over here. This is just us trying to figure out what's the smallest x and the largest x, or what's the smallest y and the largest y. But these are the little squares that we're imagining breaking this region up into. How's everybody okay? So let's take an opportunity at this point to grab an important fact. First, let's set it up. In math class, when the instructor writes recall, and then they have you recall something, that's like at the beginning of an episode where they say last time on television show. Then they show a couple of scenes. You're like, oh, wow, I don't remember that scene. That was from a long time ago. That's because they're going to be referencing that scene. And so they're just trying to bring that back to your mind. It's like, well, hey, remember that one episode where this thing happened? And you're like, oh, yeah, vaguely. It's like, oh, well, we're going to be referring to that. And then you're like, oh, okay, cool, cool, cool. So I got that in the back of my mind. So always watch. You can always tell what's going to be happening. They're going to be resolving something from previous episode. And they're going to do that by saying last time or previously on Better Call Breaking Bad of Thrones. And then they show some scenes from earlier episodes. Presumably they're going to resolve that. Not Game of Thrones. Game of Thrones never resolved anything. They just alluded to a bunch of stuff. And if I sound salty about that, it's because I am and probably will be forever. So the integral from a to b of 1 dx is x. That's the antiderivative evaluated from a to b. And then we substitute in b and a and subtract to get b minus a. The important thing that we want to notice about this is that when we integrate the function 1 over an interval on the x-axis, we get the length of that interval. when you integrate the function 1 dx, you get the length of the interval. So if I upgrade this and take the function f of xy to be the function just 1, speculate, what should this tell us? Remember, R is a region in the XY plane. And above that floor, we're just going to make a height of 1. I'm just going to put a height of 1 above every point and add up all those values. Remember what this is all built on. This is the height times the area. If the height is always 1, then whatever we get here is going to be the area. If we integrate the function 1 dx, we get the length of the interval. If we integrate the function 1 dA, we get the area of the region. We can go even further with this to integrals that we have not seen before. If we take a function of 3 variables dv and integrate the function 1, that will give us the volume of the solid W. So if we grab one of our integrals from before for this region and replace f of x with the function 1, so let's integrate, I'll just do the first one, from 0 to 9 on x, and then integrate from root x to 3, 1 dy dx. This should give us the area of this parabola-sided triangle. We're going to start by integrating with respect to y. The integral of 1 dy is just y. And then we'll evaluate from root x to 3. We've integrated dy, but we still have not integrated dx, so I have to keep writing dx. Now plug in the 3, plug in the square root of x, and subtract. So we will be integrating 3 minus root x. Now we can integrate with respect to x and then evaluate from 0 to 9. So the integral of 3 minus root x is going to be 3x minus, let's see, this is next to the 1/2. So that's going to be 3/2, so 2/3 x to the 3/2 evaluated from 0 to 9. So we'll have 3 times 9 minus 2/3 of 9 to the 3/2 minus, well, it's going to be 0. So 3 times 9 is 27 minus 2/3 of 9 to the 3/2. So the square root of 9 is 3, cubed is 27. So 27 minus 2/3 of 27 is 1/3 of 27, or 9. Now here we just plowed on through to get to the answer, number 9, which is just 9, the area of the region. But notice that this is a problem. Finding the area of this region is just a problem that we could have done in Calc 2, or even in Calc 1, at the end of Calc 1, find the area of the region. And what we would do is we would want to integrate from 0 to 9, and we just do the top function minus the bottom function. The top function being 3, the bottom function being the square root of x, and that's exactly what we're integrating down here. From 0 to 9, 3 minus the square root of x, top function minus bottom function. It fits exactly with what we were doing before. Now I remember why I wanted to do this one first. Sometimes you could just see the future. I remember now I wanted to do this one first because I knew I was going to do this next. Integrating 1 is the length of an interval, or integrating 1 is the area of the region. I knew I wouldn't be able to resist writing this line, thus leaving only room for one of these integrals. Also setting me up for, oh, too bad we're out of space, but you should check that you also get 9 on this integral. But I wanted to do the one that you definitely would have done as a student back in the day, because almost never, no one sets this integral up going in this direction. But really, it's just the same thing. Integrate from 0 to 3, top function, y squared minus bottom function, 0. I mean, the problem is it's much easier to do if you just think of it this way instead. You know what I mean? But I realize why you wouldn't want to do this. Not all of you had need for a Calc 2 instructor. And so your instructor might have marked it wrong. Who knows? They just might not have been paying attention. Like, well, why are you integrating dy? Just set up integral dx. That's the one in my answer key. It'll happen a lot less here because you'll have a lot more expertise on the part of your instructor. Any questions? Comments? Any other instructors who are watching that feel like I just threw shade at you? Don't worry, I throw shade at us too. So get over yourself. And the easiest way to come after me is say 2 minutes of information packed into 60 minutes. It's just like D&D. Any questions? You really should integrate this one. Integral from 0 to 3 and 0 to y squared of 1 dx dy. It should also give you 9. Any questions? Comments? Snide remarks. Was that too much on a Monday? I can't tell because you're all looking at me like this. I also should know that I'm not going to get any questions because I think it just clicked over to 9 o'clock. No one's going to ask any questions. In the last 5 minutes of class, I can do whatever I want and everybody will just agree to understand. I could be like, oh, here's the fundamental theorem of finitely generated abelian groups. Any questions? You'd be like, oh, nope, totally got it. Let's get the F out of here. That was the easiest one all year, Leach. See you tomorrow. And then when you walk out the door, Michael, man, I hope it's not a quiz tomorrow on the fundamental theorem of wobbling Ludwig, whatever he said. Which is funny because I don't have to go that far because you all know the fundamental theorem of calculus, but can anybody to leave today, if leaving was the only option to leave was to speak to me, the fundamental theorem of algebra, a class that theoretically y'all have passed, what's the fundamental theorem of algebra say? It's the fundamental theorem of algebra. It should be important. Maybe you should know it if you've been through an algebra class. Does anybody know it? What if I drop it back one level? What's the fundamental theorem of arithmetic? I thought you guys knew arithmetic. I'm just kidding. Y'all don't need, you can't even explain counting to me. Someone explain counting to me. That's how you get out of here today. Yeah, see? All these things that we take for granted. Mathematicians are like, oh, but why? Why that? And at this point, all the engineers understand. It's like all the engineers are like, oh, now I get why I don't know these things. I don't need to know those things to make shit work. As an engineer, I just care what works. Mathematicians like, oh, but why does this work? Engineers be like, don't care, works. Gonna go make money now. Enjoy not having free time. Anyway, that's it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.